Alright class, here we go. We're going to study our lesson on the unit circle today. So, hope you're excited. And if you aren't excited, maybe these questions might help you get your brains kind of oriented to what we're going to learn about today. So a question you can ask yourself is, have you ever thought of writing an ordered pair xy in a different form? You know, because this is probably the only way you've ever seen it. Or another question you might ask yourself is, have you ever wondered why you needed to memorize the values of sine, cosine, and tangent for certain angle measures? Because that's definitely a rigorous task. And do you think you could find the values of x and y for a given point on a unit circle, but with only one piece of information, the measure of an angle? Or are you even interested in an easier way to find the values of trig functions of angles that are greater than 90 degrees? And without a calculator. So if you thought any of those questions might apply to you, then I think you'll find this lesson pretty interesting. So a quick overview of what we're going to be looking at. We're going to extend our knowledge of what we know of right now as SOHCAHTOA, and that's basically how we've been running our process of finding out the values of trig functions. And what we'll be doing is we're going to be exploring what a unit circle is exactly, and how those xy coordinates relate to it, and the relationships between that. So that's going to help us extend our idea of SOHCAHTOA. Another main idea we're going to hit on is understanding the definition of radians. And another last main idea is going to be establishing the relationship between radians and arc length. So if you guys aren't familiar with arc length or other terms like circumference and central angle, I recommend maybe you pause the video and just kind of refresh yourself on these definitions, because we're going to be using them a little bit in this video. Alright, so now we're going to extend our idea of SOHCAHTOA. And I'm going to use GeoGebra for this because GeoGebra is excellent. And I guarantee you'll never view an ordered pair of xy coordinates in the same way ever again. Alright, so here we go. We're going to bring up GeoGebra. Here it is in all its splendor. Okay, so you can see I have a description here of what a unit circle the characteristics of a unit circle must be. So I'm going to talk through those. As you can see, we've got a standard coordinate plane here, got the y and x axis, and I've got a circle that's centered at the origin. So you can see that's the first requirement. And then the second requirement is that the unit circle must have a radius length of 1 unit. And whatever unit you choose is fine. You can choose meters, inches, feet, whatever. But it has to be of length 1 in order for it to be a unit circle. So what we commonly use unit circles for are to help us to better understand or visualize angles. So what I'm going to do is I'm going to show you some angles. Alright, and you can see here that my slider controls that angle. That's kind of, you can see here moving along the circle. And just some more terminology, this side right here that is being fixed, this is called the initial side. And the side that actually is basically the end point of the angle, that's called the terminal side. So the terminal side is the end of the angle, you know, terminator, the terminator end stuff. And then the initial side is where it starts. Alright, and as you can see, I want you to make another observation of what these angles are like. As you can see, if I move in like a negative direction, my angle moves in a clockwise direction. But if I move the other way, going in a positive direction, so see I'm in positive direction, my angle moves counterclockwise. And that's key because in any math class you take, you always assume that positive angles are in the counterclockwise direction, unless otherwise stated, obviously. But just some basics on a crash course on unit circles right now. So what I'm going to do now is I'm going to help you guys visualize the relationship between xy coordinates and these trig functions that we've been dealing with for so long. So what I'm going to do is I'm going to pull up, so you can see I've got an angle here, it's equal to 50 degrees, and what I'm going to do is I'm going to drop a perpendicular from C down to the x-axis. So there's our perpendicular, I'll even prove it to you. See, there's the right angle. Alright, so there's our perpendicular, and I'll even show. So whenever we do angles, we always make a right triangle. So here's our right triangle with our angle theta here, or beta. And if you wanted to, say, find the sine of this angle, you would say, okay, sine is opposite over hypotenuse. So f over this hypotenuse. And the length of f is right here, so nothing too fancy there. But I want you guys to think, what's the length of this hypotenuse? And remember, it's a unit circle, so the hypotenuse from the point on a circle to the center should also be a radius. So you can see that since this is a unit circle, the radius is 1, then you can basically say that the sine of this angle is going to be this length of this side here, so f over 1. So sine of this angle equals f, basically. But if you think about it without the circle, f, the value of f is going to represent the y value of the point C here. And I want you to notice, look at length of f. Here's f, and then here's the y coordinate of C. They're exactly the same. That is not by coincidence, my friends. So now we can basically relate the y value of a coordinate on a unit circle. The y value is equal to sine of theta. And if you might have felt some intuition kicking in, if we wanted to find the x coordinate of C, all we need to do is find cosine of theta, because cosine of this angle is going to be our adjacent over hypotenuse, so e over 1, or in other words, just e. So cosine of theta is equal to e, which is in fact the x value of our coordinate here, point C. So look at that. Here's the x coordinate. Here's e. They're exactly the same length. So in other words, we can relate x values to being equal to cosine of theta on our unit circle, and then the y values are sine of theta. I think that's pretty awesome stuff. I remember my mind being blown when I learned this. So anyway, that's the basics on unit circles and xy coordinates. And you might be asking yourself, well, what's the point? You know, we use SOHCAHTOA all the time and that works. Well, it only works when you know the values of your right triangle here, of these legs. But if you don't know them, then you're kind of stuck at finding the rest of the stuff, unless you know that you can find the y values by just plugging in this angle theta to sine or cosine. So now we've got a lot more options to work with. But alright, so now we know that x equals cosine of theta, y equals sine of theta on the unit circle. And there are a lot of uses for that. So just to review, if you guys need a little refresher, I brought this table back up in case you need it. We are going to be using it a lot, so I hope you still have it memorized. I even color-coded it for you, so you can notice the pattern here with sine and cosine. 3, 2, 1, 1, 2, 3. Alright, so just maybe to see if you can get this on your own, let's figure out what the xy coordinates for a point on the unit circle that has an angle of 30 degrees, or pi over 6 radians. And so remember, x equals cosine of theta, y equals sine of theta. So if we want to find the xy coordinate, we just plug in pi over 6 to each of these. And if you do that, if you have it memorized, you should get square root of 3 over 2 for x, 1/2 for y. Alright, so what exactly do radian measures tell us? Well, we'll use GeoGebra for that. So radians, if we look at a unit circle, you can see I've got a radius of 1 here. And this slider here actually changes the angle. They call it arc measure. That's the same as angle measure. And they have it in radians. But notice that as I move the measure of the radians, the arc length will change also. But notice that they're exactly the same. That is not by coincidence, my friends, because radians are in fact directly related to the arc length when on a unit circle. So let's bump this up maybe to a radius of 2. Alright, so we've got a radius of 2 now, and our circumference went up twofold as well. And so our arc measure, you know, nothing really changed here. I mean, same type of angles that I dealt with last time, but except the relationship between arc measure and arc length, you can see that these are, that the arc length is now double the measure of the angle. And notice that our radius is 2, so if I bump this up to 3, you might be able to guess that our arc length becomes 3 times the size of the angle. So that's should probably give you a clue on the relationship between radians and arc length. And just to make sure you guys have a solid understanding, I want you guys to notice that we can keep an angle the same between 3 different circles. but notice that their circumferences aren't always going to be the same, because obviously a bigger circle is going to have a bigger circumference, even though you made the same full revolution around it. So don't let yourselves be too confused by that. And notice that here's a chart just to kind of demonstrate how radians equal the arc length only when the unit circle is being used. And when you're on the other circles that are of larger size, then obviously that relationship gets a little skewed. Alright, so just to spell it out for you plainly, a radian measure of an angle is simply the length of the arc on the unit circle, which is intercepted by this angle. Another way you can think about it is if you have a central angle within a unit circle, which is measured in some sort of units like feet, so then if that angle has a measure of t radians, then the arc length of this angle is going to be t units, or t feet. Another way you can think of it is that if you have an angle that is of x radians, then your arc length is going to be equal to x radii. So like whatever the length of the radius is, however many radians you have, that's how many radii you're going to have. So you can see those words are basically the same, but you can probably suspect that's where the name radians came from. And here's a relationship to kind of model that. Alright, so, and this is in fact the formula for finding arc length. And it's a pretty handy relationship. It's pretty easy to conceptualize after looking at GeoGebra and all that good stuff. So you can see that arc length is going to be equal to the radius times theta, where theta is the angle measure in radians. That is very key here. Got to have radians. So if you want to try an example, let's say we have a circle with radius of 2 feet and an angle measure of 45 degrees. So what do you think the arc length is going to be? Well, remember, we got to have radians, so we're going to change that 45 degrees to pi over 4. So then if we multiply it by our radius, like our formula says, then we'd get 2 pi feet long for an arc length. Another example would be, let's say we have a circle with radius of 1 meter and a central angle that has an angle measure of 7.89 radians. So what do you think the arc length is? Well, it's going to be 7.89 meters. So 7.89 times 1, not too hard. But remember, a full revolution is going to be equal to 6.28 meters. That's, 2 pi. So how can we have something that's bigger than 2 pi? Is that even possible? Yes, in fact, it is. And it's actually something that happens a lot. And if you think about it, think about the globe. Does the globe ever stop turning once it's made a full revolution? I sure hope it doesn't, because we'd have quite a few wacky weather patterns if that did happen. So, if you wanted to see what an angle of, maybe 12.56 radians looks like, that's obviously more than a full revolution, all you do is divide it by what a full revolution is, and then that tells you how many revolutions you actually completed. And then if you want to go upstream, if you want to know what 3 revolutions has an angle measure of, you just take 3 times a full revolution, and then that's how many radians you get. Alright, so just remember, radians are a numeric value. It's just a number. Even though it has pi in it, it's just a number. So now that we understand angle measures that can happen beyond a full revolution, we can definitely extend the use of our trig functions now too. Alright, so just a quick review. We learned that the unit circle is a circle that is centered at the origin of the coordinate plane and has a radius of 1 unit. And also the coordinates of a point, x and y, where x is the cosine of theta and y is sine of theta. And finally, we realized that radians represent how many radii make up the arc length. And so we get arc length equals radius times theta, where theta is measured in radians. So that's our screencast for today, and I hope you learned a lot, and I'm excited to see you in class and to dive more into this later.